Welcome to this course on statistical mechanics of non-interacting and interacting systems. I am Saurabh Basu from IIT Guwahati. I will be teaching this course. A very short introduction to the course has already been given, and let us start with the basic requirements of thermodynamics. And to begin, let us understand the history, because sometimes the history actually tells a lot more than what we expect. It tells the chronological development, how this subject came into being, and at times it is very useful. So, basic notions of heat and temperature were established in as early as 1600s. Heat is thought to be associated with the motion of this constituent matter, which means that the heat is generated because of the motion of the molecules and atoms of say a gas, and temperature is the manifestation of these motion. Later, about 200 years later, Carnot he captured some of the key elements of thermodynamics, and he proposed an idealized engine with a maximum efficiency, and this efficiency of the engine is coined in terms of heat output and heat input and so on. Little later, 1850, Joule through experimentation established that heat is a form of energy, and that is what we all know as of now, that heat is a form of energy. And around the same time, Clausius and Thomson, Thomson is actually more popularly known as Lord Kelvin after he got the knighthood. He proposed first and second laws of thermodynamics. These are really important steps in understanding the behavior of physical systems. The first law, we will see all these laws in great details. For now, the first law states the conservation of energy, and the second law actually talks about the correct direction of the flow of heat. Later, the concept of entropy was put forward in 1860 by Clausius, and he said that it is a ratio of heat to temperature, and even second law says something very similar to that. We will come across these. Around the same time, Maxwell derived the distribution of molecular speeds in an ideal gas. Now, there is a very important steps. There are slow moving molecules and there are fast moving molecules, and Maxwell actually stated that they are distributed in a Gaussian sense, that is the velocity distribution is Gaussian or is bell shaped, and there is a minimum value around which most of these molecules are, their velocities are distributed, whereas very slow and very large speeds are more rare. I mean, they are rare to come across. Over the next few years, the kinetic theory of gases was developed rapidly, and the macroscopic properties of gases in equilibrium was established. This is a very important concept again. We know that the molecules are moving in a gas. So, how is the gas in equilibrium? How do we calculate the equilibrium properties? And many things about equilibrium which we will briefly come across are being discussed in this kinetic theory of gases. And in 1872, Boltzmann constructed an equation which correctly describes the time evolution of the properties of a gas. Around the same time, the molecules are thought to be uncorrelated, and uncorrelated means that these molecules, there is no intermolecular attraction, and they are just on their own moving around sort of irrespective of the presence of other molecules. And later these correlation effects have been incorporated, and this equation is known as the Boltzmann transport equation, and this is incorporated in a very nice way through the relaxation time approximation. However, we will not see that soon, and during mid 1870s, Boltzmann realized that the entropy of a gas must be proportional to the logarithm of the number of possible states of the system. This is again a very important realization. It is log times the or log of the number of possible states. So, suppose there is just a unique state of a system, say for example, a ferromagnet where all the spins are pointing in the same direction. This gives you log of 1 equal to 0, which means that the entropy of a ferromagnetic order or a system is equal to 0, as the only possible state of the system is all the spins are pointing in the same direction. And later it helped him to formulate this idea of ergodicity. We will see ergodicity, and it sort of replaces the time average of a system by the ensemble average. And Gibbs at the beginning of 1900, he introduced the notion of an ensemble, and we will see ensemble throughout this course. So, the ensemble denotes collection of many possible states of the system, and each assigned with a certain probability. Gibbs argued that the time evolution of a particular state will result in the state visiting all possible ensembles. So, if you think of a classical gas where the atoms or the molecules are randomly moving around, so you construct a large number of ensembles or rather copies of the system by taking the molecules to be distributed differently as the time progresses. And one can actually take this or consider the time average of such a system by taking an average over the ensembles, and this is called as the ergodic hypothesis, and we will see this shortly. In the early 1920s, not much work has been done in thermodynamics, because there was a very rapid growth of quantum physics, including proposal or rather putting forward the Schrodinger equation, wave particle duality, uncertainty principle, wave nature of light. I mean, whether light is a particle or a wave, it actually shows characteristics of both. Indistinguishability of particle, and this indistinguishability actually shows up in our statistical mechanics in a big way, and in fact this helps to remove a paradox which is known as Gibbs paradox that we will come across, and it has a large bearing on the study of statistical physics that we will see. Nevertheless, this progress with second law engines and the applications therein, that went on to develop the thermodynamics and also statistical mechanics. Later in 1950s, Shannon and von Neumann give new perspectives to entropy, and thereafter Bennett in 1970s he did a lot of groundbreaking computational work on thermodynamics, and that is how this study of thermodynamics evolved, and it gave input to the study of statistical mechanics. So, once again, just to remind you that thermodynamics deals with very small number of variables. They are mostly pressure, temperature and volume, and maybe the chemical composition of the gas. Now, if you make a measurement of a gas, it gives you certain values of pressure, volume and temperature, and maybe the chemical composition. Now, what is the internal structure of the gas? How are the atoms and molecules are distributed in various energy levels? That answer thermodynamics cannot give. Statistical mechanics, that is how it gives a microscopic description, so that we understand that how different particles are distributed in different energy levels, so as to give us that pressure or that volume or that temperature that we actually measure in experiments. So, let us look at some of the key points of thermodynamics, and they are equilibrium. The first thing that comes to our mind is when we talk about various things, whether we are measuring equilibrium quantities or whether we are making a physical measurement when the system is at equilibrium. Because if the system is evolving with time, then making a measurement now and making a measurement maybe 10 seconds later or 1 hour later or 3 days later, if it gives you different outcomes, that's not a correct measurement. We cannot say that that's the properties that we have measured when the system is in equilibrium. There are two main assumptions that we make regarding equilibrium, that is the values of the thermodynamic quantities, once again pressure, temperature, volume, chemical composition, etc. They remain constant over the time scale of the measurement. And in a gas, the molecules are in motion, as we have said. So, how an equilibrium can be established? So, this according to ergodic hypothesis, the time average is replaced by ensemble average, and we can still continue talking about equilibrium quantities using this hypothesis. We'll come across this. There are two kinds of equilibrium, mainly internal equilibrium and absolute equilibrium. By internal equilibrium, what we mean is that none of the properties actually change with time, and absolute equilibrium is that the properties are not only constant in time, but are independent of how the system came to equilibrium or how the equilibrium is achieved. It is independent of that. So, we talk about physical properties, and by physical properties we mean pressure, volume, temperature, or even the chemical composition, as I have said many times. As I said that there could be also magnetic moment, refractive index, etc. These are also physical quantities, they correspond to physical properties of a system. Now, not all of these are independent. Okay, so, they are connected by what is called as a equation of state. We give an example here, which we will see several times during the course of this study of statistical mechanics, is the equation of state for an ideal gas, which is P V equal to NKT, where P is the pressure, V is the volume, and T is the temperature. K with a sub B is called as a Boltzmann constant, and N is related to the number of molecules. So, temperature is an important concept in thermodynamics. In fact, the 0th law of thermodynamics is actually about temperature or thermal equilibrium. So, temperature requires of course a special treatment. We understand that because it cannot be expressed in terms of length, mass, and time. This LMT, most of the physical quantities that we come across can be expressed in terms of LM and T. However, temperature requires a different treatment. Nevertheless, if you think that temperature can be converted into energy, as Joule had said earlier, then you multiply it by the Boltzmann constant Kb, and then the energy say for example can be expressed in terms of length, mass, and time. So, in thermodynamics and statistical mechanics, temperature is expressed in the absolute scale named after Kelvin, and take a note that it is not degree Kelvin, it is just simply Kelvin. However, with other scales of temperature, that is centigrade and Fahrenheit, we use degree centigrade or degree Fahrenheit. So, the temperature in Kelvin is written as T equal to capital T equal to small t plus 273.16, where T is in Kelvin and the small t is actually in degree centigrade. So, whatever you get in degree centigrade, it can be added to or rather 273.16 can be added to that in order to get the temperature in the Kelvin scale. We talk about systems, isolated systems, we will talk about various kinds of systems which are either they allow exchange of heat or they do not allow exchange of heat. An isolated system is the one which does not allow exchange of anything. So, it is like a sealed container as you see below, and the walls are such that they do not allow exchange of heat, and this is called as an adiabatic system. Okay. So, the pressure, volume, temperature, chemical composition will remain unchanged if you immerse this container in a pool of water. Okay, nothing will change inside of what is inside the container. and it is purely isolated and it does not interact with the surrounding. However, mostly we come across systems that are partially isolated, and it is possible to partially isolate the system by attaching a piston at the neck of the container. As you see that this is a piston, and if you, so this, there is a mechanism like that which is can be pushed in, and this gas can be compressed and or it can be expanded. Like the volume in the left figure is more than the volume in the right figure, and in fact this is done by pushing this piston below, and this is we are changing the volume, and by the equation of state we are also changing other parameters in the of the system, such as there is a change in pressure. The pressure is more on the right figure than in the left figure, because pressure is inversely proportional to the volume. And so a change in temperature of the pool of water will not result in rise in temperature of the gas, because these walls that you see, they do not allow exchange of heat. So, we keep the temperature to be constant and change the volume and thereby change the pressure, and this is called as a thermally isolated system. So, we have thermally isolated it, which means that the temperature does not change, the walls of the container does not exchange heat with the surrounding, and that is why when these assembly of this piston inside and a gas inside, that is when dipped in or immersed in water, there is no change in temperature. However, not all walls are adiabatic in nature. There are walls of the container that allows exchange of heat with the surrounding, and these are called as the diathermic walls. Okay. Consider two different systems that are maintained at temperatures T1 and T2, and they are separated by diathermic walls and are brought in physical contact. Okay. So, there are two systems, one is in at a temperature T1 and the other is at a temperature T2, and they are brought in contact, and these walls actually allows exchange of heat, and it is easy to see that each of the system or each of the components will come to a new equilibrium at a common temperature T. They cannot maintain different temperatures, they have to come to a common temperature which is different than T1 and T2, and it is actually in between T1 and T2. So, suppose T1 is greater than T2, so the common temperature will be lesser than T1, but greater than T2. Now, consider three such systems A, B and C. It is easy to see that if A is in thermal equilibrium with B and B is in thermal equilibrium with C, then A is in thermal equilibrium with C, and this is known as the 0th law of thermodynamics. Sounds very trivial, but however, in those days when the subject was in the nascent stage and things were developing, even this got a name that is called as the 0th law of thermodynamics. So, it just simply says that if there are number of components or rather number of different systems that are in thermal equilibrium with each, one is in thermal equilibrium with another, then they all are in thermal equilibrium, and they maintain a common temperature when they are brought in either physical contact or they are connected by some contact that allows exchange of heat. So, what are the different thermodynamic processes that we come across? There is a spontaneous process, there is an irreversible process, and there is a reversible process. And let us see what a spontaneous process is. A spontaneous process occurs when there is no external intervention. Okay. There is no external agency that does anything and it happens on its own. For example, if you keep a piece of iron in open air, it gathers rust. Okay. And this will automatically happen, and of course, moisture is responsible for that, but it just will happen without any external intervention by us. So, gradual cooling of a hot cup of coffee, if you keep a cup of coffee for a long time, it will attain the temperature of the room, it will get cooler, and this is a process again which is spontaneous. Let us talk about an irreversible process. This is important. Consider a gas to be in an initial state described by this P1, V1 and T1. Okay. The pressure, volume and temperatures have some values which we call as P1, V1 and T1. Now, what you do is that you suddenly, that is very quickly or rapidly, you change the volume to V2 by pushing the piston that we have shown. So, there is a gas there and there is a piston that is fitted to, and you suddenly push it down or you pull it up, does not matter, and then wait for the equilibrium to achieve. The system will come to a new equilibrium, say the pressure, temperature and volume are given by P2, V2 and T2 as we sort of pressure, volume and temperature, they have acquired new values here. Now, you consider the piston to be brought back to its original position such that the volume is V1. So, it was V1 earlier, you quickly push it down or pull it up such that the new volume becomes V2, and then you take the piston exactly to where it was such that the volume becomes V1. Now, this sudden process involves friction and other dissipative phenomena such as which can this dissipate as heat, making this process irreversible. So, this process is irreversible. So, the P1 and T1 which were the initial values of pressure and temperature, they are never achieved even if you have pulled the volume to this original value which is V1, and this is an irreversible process. So, an irreversible process will occur when you do it very quickly or you change say one of the parameters very quickly, which will involve non-equilibrium processes, that is in going from P1, V1, T1 to P2, V2 and T2, there are a lot of non-equilibrium processes that are involved. So, even afterwards when you bring it back to V1, the volume back to V1, still the other parameters which are P1 and T1, pressure and temperature, they do not come back to the original value. Now, what is a reversible process? Again, consider a gas in the initial state is described by P1, V1 and T1. Now, very slowly change the volume to V2. No, this is not rapidly, this is really slowly, pardon me for this typo. So, you do this very slowly by slowly pushing or pulling the piston. So, at every step the change in internal pressure is same as that of the applied pressure. Now, again do the same thing, that is bring back the piston so that the original volume is regained or recovered, which is V1. So, this slow or the quasi-static process does not involve any dissipative phenomena and making the process reversible, so that you again get back the same pressure and temperature that you started with, which are P1 and T1, and this is an example of a reversible process. Let us discuss three laws of thermodynamics, namely the first law, the second law and the third law. We start with the first law of thermodynamics, and it tells that in the simplest form, as we have already seen, it states the conservation of energy. Okay. Maybe a more technical version tells you that there exists a function of state, there is an important word, or it is also called as a state function. The same thing. U, this is called as the internal energy. So, the internal energy is the content of energy due to the the molecular motion, etc. So, that if an amount of energy E is supplied, capital E is supplied to an isolated system, transforming it from one equilibrium state alpha to another equilibrium state beta, then this E is equal to the change in the internal energy corresponding to these equilibrium states alpha and beta. So, E is equal to U of beta minus U of alpha, and this process does not depend upon the way in which E is supplied. What I mean is that this E could be supplied by an electrical circuit, or this could be by sort of supplying maybe heat and so on by putting a Bunsen burner. So, it is independent of how it is supplied. The this energy E that is supplied is will cause the state function or the internal energy to be the difference between the two states, equilibrium state, the alpha and beta. Okay. So, irrespective of which path it followed in coming from one equilibrium state to another equilibrium state, that would not matter in this case. So, the discussion above ascertains that U is a state function, also called as a function of state. In a general sense, U may depend upon volume and other thermodynamic parameters. Okay. If a system is not thermally insulated, then heat can flow through the walls of the container, and the total energy supplied will now be the sum of the heat supplied to the system and the work performed on the system. Now, the reason that this is marked in red is because of a sign convention that we would discuss later, that is this work done on the system and work done by the system. In one case it takes a positive value, and in another case it takes a negative value. Now, what we are interested in at this stage is that now this energy that we wrote down earlier is equal to some Q plus W, where this Q is the heat and W is the work. So, even if this quantity does not depend upon how the equilibrium is achieved, will show that W actually depends upon path that is followed, because it is related to the different heat could be actually absorbed or given by the system, I mean given up by the system, either its heat is gone into the system or heat is left by the system. So, it is heat also can be either the system has a larger temperature during the process, or the temperature reduces and so on. So, this tells us that the non-exactness of the work done, and suppose an ideal gas is compressed at a constant temperature from an initial state alpha to beta as shown below. So, you see that there is a PV diagram, and we are showing an equilibrium state alpha here and a beta here. So, it goes in this path, and the work done would be given by minus PDV. This minus sign will be discussed, as I said earlier, that the sign convention that is usually followed in thermodynamics is an important thing. It would be discussed, and it is nothing but the PDV, where P is the pressure. You can write it with a capital P if you like. So, it is a PDV, and it is nothing but if you use the equation of state and use this thing as say for example nRT by V, then is a dV over V, and you get a log of that, and because of the minus sign you get a log V alpha by V beta. So, that is the work done if you take the gas from the equilibrium state alpha to an equilibrium state beta by keeping the temperature to be constant, because you see here the temperature is constant. Now, if instead of taking it directly from alpha to beta, if you take it through this state gamma and then to alpha to gamma and gamma to beta, then it is no longer it is given by this nRT log V alpha by V beta. There are different amount of heat that are extracted by the gas, and it is no longer just the final state and the initial state, and even though internal energy is a property of the system, but the work done actually depends on the process. And the convention that follows is that for such processes that depend upon the path, we write it with this kind of a delta, and the ones that are the state functions their change is denoted by full differential. Finally, let us talk about the specific heat. Specific heat is defined as a heat required to raise the temperature of a system by 1 degree. Okay. And we know that it differs when the process is performed, or rather this change is performed, heat is given at constant pressure or at constant volume, and we are able to define two quantities such as CV and CP. And in a lot of situations, rather particularly in ideal gas, there is a simple relation between CP and CV. We will continue with the discussion of second law, and then we will do the third law, and then we will get on to a more intricate phenomena in thermodynamics, and then we will of course go to statistical mechanics.